Hey, what's up you guys? This is Kaggle Code Review Show and Ilarian Garbuzov. Today we'll do the house prices advanced regression techniques Kaggle competition. Let's go! Pow 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 pow! Okay, first of all, let's see the description of the competition. So you see it on the screen. The competition name is House Prices Advanced Regression Techniques. So it's a regression competition, and we need to predict sales prices and practice feature engineering and different models. So let's see the competition description. Ask a home buyer to describe their dream house, and they probably won't begin with the height of the basement. And in the competition, we would have all the features about the houses. So with 79 explanatory variables describing every aspect of residential homes, in Iowa, this competition challenges you to predict the final price of each home. Let's see the data. So we would have training set, the test set, the description text file, and the submission CSV file. We got different features as sale price. Sale price is not a feature, sorry about that. Oops, it's target. The building class, the general zoning classification, different features, numeric features, categorical features, like heating quality and condition, sale type of sale, condition of sale. So it's all the features you got in Zillow.com. You'll find at Zillow.com when you look for different houses. Okay. So let's dive into the data and look how we will do the feature engineering and the modeling part. Let's go. We would review the code of, from one of the Kaggle members. The name of the Kaggle notebook would be stacked regression, top 4% on the leaderboard. So a little about the Kaggle member. It's a Serigne, quant data scientist in Paris. So let's dive in to the code and do all the data science magic. We would use, as usual, data callout because it's simple to share and good for data science, different data science projects. So this competition is really about feature engineering, about inputting missing values, transforming features, label encoding, the box-cox transformation, and about regressions. Okay. So first of all, we need to load the data. We would use Kaggle API. Let's check our runtime. Okay, this is a GPU file. Let's look to the Kaggle competitions list. And find our competition. It's called House Prices Advanced Regression Techniques. And load, finally load data. When we load the data, let's import libraries, NumPy for linear algebra, pandas for processing CSV files, Matplotlib, Seaborn, and SkyPy for statistics. Okay, let's load the libraries. And finally load the data. Let's look for column values of the data. So we see different features, and let's dive into the head of the data set. So we see different values of different features and our target value, sale price. Okay. For the test data, I think we'll see the same, but without the target, without the sale price. Okay, let's check the shapes of the data. So we've got 1460 in the train data and 1459 in the test data set. And 81 columns in the train data and 80 columns in the test data. And after dropping the ID, it would be one less. Okay, then let's do the data processing part. And first of all, let's explore the outliers. So here we see the plot, sale price and living area. And at the bottom right, we see the extremely large living area for a low price. So in this data set, we see the linear relationship, and it's not useful to have this outlier. So let's drop it. And we have warning that the outliers removal is not always safe, okay? Let's explore the target variable. And the distribution of the target variable. It's not, we can plot a QQ plot of the target variable of the sale price. And we see the distribution mu and sigma, and plot the normal distribution. And on the QQ plot, we see that it's not really like normal distributed, and it's skewed, okay? And we would use the linear models in this regression. And linear models love normally distributed data, so we need to transform this variable and make it more normally distributed. And we will. Okay, let's see the distribution of the target variable. So we would use, we would plot it, and this is a normal distribution, and this is a distribution of the target variable. We would use the QQ plot, and we see on the plot the skewness of the target variable, and really it's not that normal distributed. And we know that linear models love normally distributed data, so we need to transform the target variable and make it more normally distributed. So we would use the logistic transformation for the target variable to make it more normal distributed. And after the logistic transformation, we see that skewness has gone, and we see the QQ plot. This skew seems now corrected, and the data appears more normally distributed. So let's go for the features engineering. Let's first concatenate the train and the taste data, and see the missing data, okay, by the missing ratio. We would assume all null values and see the missing ratio. And what we see that we've got really a lot of missing data in our concatenated data set. So we need to fix it. Okay, let's see it on the plot, on the bar plot, and we see different missing values by feature on the histogram. Let's look to the data correlation with the target value, with the sell price. And we understand that we need to fill in the missing values. Okay, let's input the missing values. And we would do it one by one. For the pool QC, so the description says NA means no pool. Let's fill it in. And we'll do the same for the miss feature, LA, fence, fireplace, lot frontage. What about the lot frontage? We'll fill in missing values by the median of the neighborhood. So we need to group by neighborhood. And with the lambda function, fill missing values with the median value. We'll do not the same. We'll put none in the garage type, replacing missing data. We would put in 0 for replacing missing values garage air build, garage area, and garage cars. Since no garage means there is 0 cars inside garage. 0 for basement features. Missing values are likely 0 for these features. For all these basement related features, we'll put in a none. And for NA in mass VNR area and mass VNR type, we'll put none and 0. For the zoning, we would we'll put in the most common value. And since for this for the utilities, this categorical feature all records all pub except for 1, so we don't see the correlation with the target value, and we can safely drop it, remove it from the data set. For the functional data description, say NA means typical, so we fill NA with type. Do fill in the mostly used feature in electrical SBR care, so we can put it in. Do the same for the kitchen wall and exterior features. For the sale time, we will fill in most frequent. And for MS subclass, we would fill NA with none. So let's check remaining missing values. And we see that we got no missing values after our engineering, after we put in all the missing values in our data set. So let's let's start the feature engineering and the transformation of all the features. So we can transform numerical features that are really categorical. It's about subclass. We would apply it as a string. Overall cond as a string, and year sold and month sold. Okay, as soon as we fill in the missing values, let's do the label encoding. We'll do it with the sklearn preprocessing. We would import label encoder. So we would encode target labels with values between 0 and number of classes. We choose the columns and process the label encoding for all the columns in the for loop. Okay, let's do it. And let's look to the shape of the data. It's 2917 and 78 features. And let's look to the head of our date frame. So we see all our features that we encoded with the target labels. That's how our date frame looks like after the label encoding. Okay. Since array-related features are very important and we've got a linear relationship between array-related features and the target, we add one more feature, which is the total area of the house. Okay, adding total square footage feature to our data set as a total square footage. And after that, let's look for the let's look how features are distributed, and we will see that they are skewed. And so we see that their numeric features are skewed, and more weight in the left tail of the distribution. So we need to use the box-Cox transformation for the skewed features to make it more really normal distributed, because linear regressions love normally distributed data sets. We use we would use features that are really messy. I mean really messy skewed, and we would use the box-Cox, and you see how we would do it for each feature. And after that, we can get the new train and test sets and start our modeling part. Okay, let's start the modeling part. And we'll start it with importing the libraries. From sklearn, we would import linear models, ElasticNet, Lasso, Bayesian Ridge. We would import ensemble with a random forest and gradient boosting, and kernel reach, pipeline, preprocessing, model selection for the cross-validation, and k-fold, train test split, and metrics. And we would import XGBoost and light GBM to compare. Okay, let's do it. And before that, let's look like the trained dataset. And here it is. And we see all the dummy values and the shape of the trained dataset. It's 1458 and 220 features because of the dummy values. Let's split it with 5 folds, so the n folds would be 5, and define the cross-validation. So we would use a cross-val score of sklearn with a shuffle and 5 folds, and define the RMSE by cross-val score evaluated with a cross-validation, train values and predicted values, and the scoring would be negative mean squared error on the 5 folds. Okay, so it would be our cross-validation function. So let's do the base models. Lasso regression with a make pipeline, so it's a robust scalar, and cause we need to make it more robust. So we would use the robust scalar on the pipeline. And lasso regression. ElasticNet regression, the same, robust scalar and ElasticNet on the pipeline with alpha, L1 ratio, and random state. Kernel reach regression, gradient boosting regression. You see all the coefficient, estimators, learning rate, depth of the tree, max features, leaves, sample splits, and the Huber loss, and the XGBoost with its hyperparameters, and light GBM. And let's see how these base models perform on the data by validating the cross validation function on them. So okay, we've got our scorer, RMS LECV that we made a step earlier. Here it is. And let's see how these models perform. Okay, let's go. So our Lasso score, ElasticNet score, kernel reach score, GBoost score, gradient boosting. So while we are waiting for gradient boosting, I'll do the XGBoost and light GBM. And we would wait a little. Now we can let's see how these models perform and the score. So the lasso score is 11, elastic 11, 15. Elastic net score is 11, 16. 11 kernel rich classifier rich score 1153. Gradient boosting score 1167. XGBoost score 1150. And light GBM score is 1176. And so the best score right now is lasso score, okay? So it's the base model, but we need to it's base models. Let's do the stacking, okay? So we begin with the simple approach of averaging base models while stacking. We will build a new class to extend sklearn with our model and also to leverage encapsulation and code reuse. So we would do the new class averaging models for the stacking, and at prediction we would take the mean of predictions of models. So we just average 4 models here. Okay, so we can see the score for average models and compare it to the base models. So we would wait for it and see you. Okay, here is the result for the average base model score. It's 10.1087. So it seems the simple stacking really improves the score, because our best score was 1150. No, sorry, oops, 1115. And right now it's 1087 for the simple stacking. Okay, so the less simple stacking is a meta model. When we split the total training set, it's in different sets. Train and hold out, train several models on the first part, test these base models on the second part, and use the predictions for the meta model and make the predictions from that. Okay, let's here is the graph of our meta stacking. That's how we would do. We would learn, predict, make a new feature, and learn our last model on the predictions, and predict for the with this new feature. So that's how it looks in the code. It would be the new class taking average models. So it's got base estimator, regressor mixin, and transformer mixin. So to make the two approaches comparable, we just average eNet and GBoost. Then we add lasso as a meta model. So the base models would be eNet, GBoost, and KRR, and the meta model would be our best base model, so the lasso. And our score would be, as usual, RMSLE on the cross validation. And right now we're waiting for the staking average models score. And finally, we've got a beta score by adding meta learner, so it's 0.1081. And let's ensemble a stacked regressor, XGBoost and LightGBM. So we would add XGBoost and LightGBM to the stacked regressor defined previously. So the stacked regressor, stacked averaged models, and the prediction. And here is the score. XGBoost and the prediction here is the score, and LGBM, here's the score, and LMS LE score on train data, here it is. So it's better than on our base model and even on our ensemble models. So on the final ensemble prediction, we would take the stack predictor, XGBoost predictor, and the LightGBM predictor, and submit our ensemble predictions. So if you find this notebook helpful or just like it, like button. And if you want me to show you how I would make it with neural networks, make a comment and subscribe, please. So push the like button and see you in the next code review. Bye.